Let me ask you something that sounds simple but isn't. Have you ever seen infinity? Have you ever touched it, measured it, experienced it in any direct way? You probably haven't. Nobody has. And yet infinity is everywhere in our descriptions of the universe. Infinite space, infinite time, infinitely many particles, infinitely small points. We use the word so casually, so confidently, that we forget to ask the most basic question of all. Is infinity real? Or is it something we invented because our mathematics needed it, and then we convinced ourselves the universe must contain it too? I have spent decades working with equations that contain infinities. Quantum field theory, general relativity, string theory, black hole physics. Infinities appear in all of them. And I can tell you something that might surprise you. Physicists don't love infinity. We fear it. Every time an infinity appears in our calculations, it's usually a sign that something has gone wrong, that our theory is breaking down, that we've pushed our equations beyond the domain where they actually describe reality. Infinity in physics is almost always a symptom of disease, not a feature of health. But let me start at the beginning. Let me tell you how infinity entered human thought, and why it's been causing trouble ever since. The ancient Greeks were the first to take infinity seriously, and they were immediately suspicious of it. Zeno of Elea constructed his famous paradoxes specifically to show that infinity leads to absurdity. Consider his most famous one, Achilles and the tortoise. The tortoise gets a head start. Achilles runs faster, but to catch the tortoise, he must first reach the point where the tortoise started. By the time he gets there, the tortoise has moved a little further. Now Achilles must reach that new point. But by the time he does, the tortoise has moved again, and so on, forever. An infinite number of steps. Zeno's conclusion was that motion is impossible. Achilles can never catch the tortoise because he would have to complete an infinite number of tasks first. Now we know Achilles does catch the tortoise. We see it happen. So what went wrong with Zeno's reasoning? The standard answer is that Zeno didn't understand infinite series. The sum of an infinite number of decreasing intervals can be finite. 1/2 plus 1/4 plus 1/8 and so on equals 1. Not infinity. Mathematics resolved the paradox. But here's what most people miss. Mathematics resolved it by accepting infinity into its framework, by saying yes, there really are infinitely many steps, but infinitely many steps can happen in finite time if each step takes proportionally less time. Do you see what happened there? We didn't eliminate infinity. We domesticated it. We made it respectable. We said infinity is fine as long as it behaves, as long as infinite sums converge to finite answers. But the question of whether anything infinite actually exists in the physical world, that question was quietly set aside. Aristotle saw this problem clearly. He distinguished between what he called potential infinity and actual infinity. Potential infinity is a process that can continue without end. You can always add one more, you can always divide again. There's no largest number, there's no smallest fraction. But this is just a process, an operation you can repeat. It never reaches a completed infinity. Actual infinity would be different. It would be a completed infinite collection, existing all at once. Aristotle said potential infinity is real, but actual infinity is not. You can always count higher, but there is no infinite number you eventually reach. This distinction dominated Western thought for 2,000 years, until Georg Cantor came along and broke everything. Cantor was a German mathematician working in the late 19th century, and what he discovered about infinity still disturbs people today. He showed that actual infinity not only makes sense mathematically, but that there are different sizes of infinity. Some infinities are bigger than others. Think about that for a moment. We're not talking about large, finite numbers that seem infinite to us. We're talking about genuinely infinite collections that differ in size. The infinity of natural numbers, 1, 2, 3, 4, and so on, is the smallest infinity. Cantor called it Aleph null, but the infinity of real numbers, all the points on a line including irrationals like pi and the square root of 2, is strictly larger. There are more real numbers than natural numbers, even though both collections are infinite. How can one infinity be larger than another? Cantor proved it through his famous diagonal argument. Suppose you try to list all real numbers between 0 and 1. Any list, no matter how cleverly constructed. Cantor showed you can always construct a new real number not on your list. You just take the diagonal digits and change each one. The new number differs from the first number in the first decimal place, from the second number in the second decimal place, and so on. It's not on the list. Therefore, no list can contain all real numbers. Therefore, the real numbers are uncountable. Therefore, the infinity of real numbers is larger than the infinity of natural numbers. Cantor didn't stop there. He showed there are infinitely many sizes of infinity, an infinite hierarchy of infinities, each larger than the last. The power set of any infinite set is strictly larger than the original set. You can always go bigger. There is no largest infinity. This was revolutionary. It was also deeply controversial. Many mathematicians thought Cantor had gone mad. Henri Poincaré called his work a disease from which mathematics would eventually recover. Leopold Kronecker called Cantor a corrupter of youth. The opposition was fierce. Cantor suffered repeated mental breakdowns and died in a sanatorium. But mathematically, Cantor won. His set theory became the foundation of modern mathematics. Actual infinities are now standard. Every mathematician works with them daily. The question of whether they're real, whether they exist in any physical sense, that question remains unanswered. Now let's talk about physics, because physics has a very different relationship with infinity than mathematics does. In mathematics, infinity is a tool, a powerful, elegant, indispensable tool. Mathematics can handle infinities just fine as long as you follow the rules. But physics is supposed to describe the actual universe. And the actual universe, as far as we can tell, doesn't like infinities very much. Consider the most famous infinity in physics, the singularity at the center of a black hole. According to general relativity, when a massive star collapses, its matter compresses into a single point of infinite density, infinite curvature of space-time. All the mass in zero volume. This is what the equations say. But does anyone actually believe this? Does anyone think there's really a point of infinite density sitting at the center of every black hole? I don't, and neither do most physicists if you press them. The singularity is not a prediction of physics. It's a confession of ignorance. It's the equation saying we don't know what happens here. Our theory breaks down. General relativity stops being valid at these extreme conditions. Something else takes over, presumably quantum gravity, which we don't fully understand yet. The same thing happens at the Big Bang. Run the expansion of the universe backward in time, and you reach a point where the entire universe was compressed into a singularity. Infinite temperature, infinite density, the beginning of time itself. But again, nobody really believes this is what happened. The singularity is a placeholder. It marks the edge of our knowledge, not a feature of reality. Quantum field theory has its own infinity problem, and this one is even more troubling because we had to develop elaborate techniques to hide it. When you try to calculate something simple, like the probability of two electrons scattering off each other, the straightforward calculation gives infinity, not a large number. Infinity. The answer is meaningless. The technique we use to fix this is called renormalization. It's clever and it works, but it's also deeply unsatisfying if you think about it carefully. What we do essentially is subtract infinity from infinity and declare the answer finite. We introduce artificial cutoffs, calculate our answers, and then argue that the physical predictions don't depend on where we put the cutoffs. It works. The predictions match experiment to extraordinary precision, but the infinities are still there, lurking in the formalism. We've hidden them, not eliminated them. Richard Feynman, who helped develop these techniques and won a Nobel Prize for them, called renormalization a shell game, a way of sweeping the infinities under the rug. It works, he said, but it's not intellectually satisfying. We're still waiting for a deeper theory that doesn't need these tricks. Let me tell you about something I've worked on that speaks directly to this question of whether the universe contains actual infinities. The holographic principle. The holographic principle emerged from studying black holes, specifically from trying to understand black hole entropy. Entropy is a measure of how many different microscopic arrangements could produce the same macroscopic appearance. For an ordinary object like a box of gas, the entropy is proportional to the volume. More space means more places to put particles, which means more possible arrangements. But Jacob Bekenstein discovered that black hole entropy works differently. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This is strange. It's as if all the information about what fell into the black hole is encoded on its surface, not distributed throughout its interior. I helped develop this into the holographic principle, the idea that the maximum information content of any region of space is proportional to the area of its boundary, not its volume. Think about what this means. If you have a region of space, there's a maximum amount of information it can contain. Not infinite, finite, bounded by the area of the surface. This suggests something profound. The universe might have a finite information content, not infinite, finite. There might be a cosmic limit to how much information, how much complexity, how much stuff can exist in any region of space. If this is true, then actual infinity doesn't exist in the physical universe. The universe is finite, not in the sense of having an edge, but in the sense of having a maximum information content. Now this is still speculative. We don't have a complete theory of quantum gravity. The holographic principle might be wrong or might need modification. But it suggests a direction. It suggests that when we finally understand physics at the deepest level, infinities might disappear. They might turn out to be artifacts of our incomplete theories, not features of reality. But let me complicate things, because there's another place where infinity seems to appear, and this one is harder to dismiss. The question of whether the universe itself is infinite. When we look at the universe, we see it's expanding. Space itself is stretching, carrying galaxies away from each other. Looking backward in time, the universe was smaller, denser, hotter. About 13.8 billion years ago, it was in the hot, dense state we call the Big Bang. But here's the question. Is the universe infinite in extent or merely very large? The observable universe is finite. There's a cosmic horizon beyond which we cannot see, because light from more distant regions hasn't had time to reach us since the Big Bang. This horizon is about 46 billion light-years away in every direction. But what lies beyond the horizon? More universe? If so, how much more? Does it go on forever? Current measurements suggest that the universe is either infinite or very close to it. The geometry of space appears to be flat, or so close to flat that we can't measure any curvature. A perfectly flat universe would be infinite in extent, but we can't actually prove the universe is infinite, because we can only observe a finite portion of it. For all we know, the universe might curve back on itself very gently, closing into a finite but unbounded space, like the surface of a sphere but in 3 dimensions. Here's what I find fascinating. We speak so casually about an infinite universe, but we've never proven it. We can't prove it. The evidence is consistent with an infinite universe, but it's also consistent with a very large finite universe. And yet cosmologists routinely treat infinity as if it were established fact. Even more troubling is what an infinite universe would imply. If the universe is truly infinite and matter is distributed roughly uniformly throughout it, then anything that can happen will happen, not just once, infinitely many times. There would be infinitely many copies of Earth, infinitely many copies of you, infinitely many copies of this exact moment, repeating forever across an infinite cosmic canvas. Some cosmologists embrace this. They say yes, in an infinite universe, you exist infinitely many times. Your doppelgangers are out there, living slightly different lives, or exactly the same life, over and over. But is this science, or is it a philosophical commitment disguised as a cosmological conclusion? We've taken an assumption that the universe is infinite, which we cannot verify, and derived spectacular consequences from it. But the foundation is uncertain. There's another infinity that haunts modern physics, and this one comes from quantum mechanics. The many worlds interpretation. According to standard quantum mechanics, when you measure a quantum system, you get one result out of many possibilities. Before measurement, the system exists in a superposition of all possible states. After measurement, it's in just one. This is the notorious collapse of the wave function. The many worlds interpretation, proposed by Hugh Everett in 1957, offers a radical alternative. There is no collapse. Instead, every possible measurement outcome actually occurs. The universe splits. In one branch, you see the electrons spin up, In another branch, you see it spin down. Both branches are real. Both versions of you are real. They just can't communicate with each other anymore because they've diverged into separate branches of reality. If this interpretation is correct, then reality is constantly branching. Every quantum event, everywhere in the universe, creates new branches. The number of branches grows exponentially. After billions of years of quantum events throughout a vast universe, the number of branches would be inconceivably large, effectively infinite, if not actually infinite. Some advocates of many worlds embrace this. Sean Carroll, a physicist I respect enormously, argues that many worlds is the most parsimonious interpretation of quantum mechanics. The wave function is all there is. It never collapses. It just evolves according to the Schrödinger equation. Simple, elegant. And it implies infinitely many versions of you. But is this real? Or is this an infinity we've introduced through interpretation rather than discovered through observation? The many worlds interpretation makes exactly the same predictions as standard quantum mechanics. There's no experiment that could distinguish them. We're choosing to believe in infinite branching worlds not because evidence forces us to, but because the mathematics is clean. I'm not saying many worlds is wrong. It might be right. But it's striking how willing we are to accept the existence of infinitely many unobservable parallel worlds on the basis of mathematical elegance. We wouldn't accept infinitely many unobservable angels on the basis of theological elegance. Why do we treat physics differently? Why do infinities appear in our theories at all? Here's one answer that I find compelling. Infinities appear because our theories are approximations, and approximations often involve idealizations that don't literally exist. Consider a simple example. The electric field of a point charge. According to classical electromagnetism, a point charge creates an electric field that becomes infinitely strong as you approach the charge itself. Right at the location of the charge, the field is infinite, but there are no point charges in nature. Electrons have a finite size, or more precisely, they're quantum objects that can't be localized to a mathematical point. The infinity in the classical theory is an artifact of the point charge idealization. It's not telling us about reality. It's telling us that our idealization has broken down. The same logic might apply to every infinity in physics. Singularities in black holes might be artifacts of treating spacetime as continuous when it's actually discrete at small scales. Infinities in quantum field theory might arise from pretending that fields exist at every point in a continuous spacetime, when spacetime itself might be granular. The infinite universe might be an extrapolation of what we observe locally to regions we've never seen and never will. If this is right, then infinity is not a feature of the universe. It's a scar, a mark left by our theory's failure to fully capture reality. And as our theories improve, the infinities should heal. They should be replaced by very large but finite numbers, or by structures so different from our current concepts that the question of finite versus infinite no longer applies. But I don't want to sound more confident than I should. The honest answer is that we don't know whether infinity exists in the physical world. We really don't. Despite centuries of mathematics and physics, the question remains open. There are serious physicists who believe infinity is real. Max Tegmark argues that the universe is literally a mathematical structure, and mathematical structures routinely contain infinities, so the physical universe contains infinities too. David Deutsch argues that the many worlds interpretation is correct and reality consists of infinitely many parallel universes. These are not fringe figures. These are respected researchers making serious arguments. There are equally serious physicists who believe infinity is not real. The finitists in mathematics argue that even mathematical infinity is a useful fiction rather than a genuine entity. Some quantum gravity researchers expect that spacetime is discrete at the Planck scale, eliminating the infinities that arise from continuous geometry. The holographic principle suggests a finite information bound on any region of space. I find myself somewhere in between. I'm suspicious of infinity. I've seen too many infinities in physics that turned out to be mistakes, artifacts of incomplete theories, signs that we were asking the wrong question or using the wrong framework. But I'm not confident enough to declare that infinity doesn't exist. The universe might surprise us, it often does. What I can say is this: we should be more careful about infinity than we usually are. We should distinguish between the mathematical concept of infinity, which is well defined and consistent, and the physical claim that infinite quantities actually exist in the universe, which is unproven and perhaps unprovable. We should recognize that many of our most spectacular cosmological conclusions, infinite parallel worlds, infinitely many copies of you, an infinite past or future, rest on assumptions about infinity that we cannot verify. There's something almost religious about our relationship with infinity. It inspires awe and terror in equal measure. The infinite universe makes us feel small. The infinite future promises either eternal hope or eternal despair. Infinite divisibility suggests that reality has no bottom, no foundation, no ultimate atoms to stand on. Infinity is the secular version of the divine, something so far beyond human comprehension that we can only gesture at it with symbols. Maybe that's why we're so reluctant to let it go. Maybe infinity serves a psychological function, filling the space in our minds where God used to be. The eternal, the unlimited, the boundless. We need something to be beyond us, something to mark the horizon of human understanding, something to remind us that we are small and the universe is vast. But science isn't supposed to work that way. Science is supposed to follow the evidence, not our emotional needs. And the evidence for infinity, real physical infinity existing in the actual universe, is weaker than most people realize. We've assumed it more than discovered it. We've needed it more than proven it. Let me end with a thought that might seem strange coming from a physicist. Maybe the question of whether infinity exists is not a physics question at all. Maybe it's a philosophy question, or a mathematics question, or even a question that has no answer. Physics tells us about the structure of the universe, about matter and energy and space-time and forces. But whether the mathematical abstractions we use to describe these things, including the abstraction of infinity, correspond to anything real that might be beyond what physics can answer, physics uses infinity. Whether infinity exists is another matter. Mathematicians will continue to work with infinite sets and prove theorems about them. That's fine, that's mathematics. Cosmologists will continue to model an infinite universe because the mathematics is convenient. That's fine too. But when we claim that infinity actually exists, that there really are infinitely many parallel worlds, or infinitely many copies of you, or an infinitely long future, we've stepped beyond what our evidence supports. I've spent my career pushing the boundaries of theoretical physics, speculating about extra dimensions, the landscape of string theory, the holographic nature of space-time. I'm comfortable with speculation, but I try to be honest about what's speculation and what's established fact. And the existence of infinity is speculation. It might be true. It might be false. We don't know. What I do know is that the universe is stranger than we thought, but possibly not as infinite as we assumed. The boundaries of knowledge are real, even if the boundaries of the universe are not. And sometimes the most honest answer to a deep question is the simplest one. We don't know. Not yet. Maybe not ever. And maybe that's not a failure. Maybe that's just what it means to be finite beings trying to comprehend an incomprehensible cosmos. We reach for infinity because we can imagine it. But imagination is not existence, and the question remains open, as it always has, as it perhaps always will. Does infinity exist? I don't know. Nobody knows, and anyone who tells you otherwise with complete confidence is not telling you what physics has proven. They're telling you what they believe, which is fine. Belief is human, but belief is not knowledge. The universe keeps its secrets. Infinity might be one of them.